Well, one of the best ways of testing your understanding is to apply it to new problems. And if you can successfully solve a problem that you have not seen before, that means that your understanding is flexible in nature, in the sense that it is not anchored in the problems that you've solved before, but it can be transferred to new problems. And so with that perspective in mind, what I'm going to do is pose a few problems, and problems that quite likely you've not seen before. Right, so let's start with a problem which will test your understanding of and your ability to apply continuity equation. So what we have here is a n-type semiconductor, and the n-type semiconductor has two ohmic contacts, ideal contacts here, ideal ohmic contacts. And the definition of our ideal ohmic contact, one of the properties of an ideal ohmic contact is that the excess carrier concentration delta N and delta P are 0 here. So this n-type semiconductor with a doping of 10 to the power 17 per centimeter cube is both ends of it are grounded, which means that there's no voltage applied to it. But what we have is that in the middle of the n-type semiconductor, we have a generation rate. We have a generation rate G equal to G naught delta X. So it's a generation only at X equal to 0. And it's something like, for example, let's say we have a laser and it absorbs it only, let's say, at one particular point, then we'll have generation only around that particular place here. All right, so the generation G equal to G naught delta X. G naught is given as 10 to the power 16 per centimeter cube per second. And the semiconductor is silicon with mobility, hole mobility of around 400, electron mobility of 1000, and a hole recombination lifetime of 10 microsecond. The length of the n-type semiconductor is 2 micron, and the generation rate occurs right in the middle here. And so that's the problem. So n-type semiconductor with a generation, with a narrow generation right in the middle, and no voltage is applied to it. And what you have to do is determine all these quantities here. You have to determine what is the electron density, what is the hole density, what is the hole drift current, what is the hole diffusion current, and similarly what is the electron drift current and what is the electron diffusion current. And all these quantities have to be determined by assuming that the semiconductor is in steady state. Right, so that's the problem. And so basically a test of, as I said, your ability to apply continuity equation and make suitable approximations and obtain the answer. And now I'm not going to post the solution to this particular problem, because then people who see this problem later on will be tempted to see the solution rather than solve it themselves. So I would like you to solve it by yourself, and if you have doubts regarding your solution, you can mail me your solution, and I'll try and give the feedback. All right, so